Hello everybody. In this video we are going to be looking at the solutions to the college prep sound homework problems 16 through 20. Let's take a look at problem 16. We have a 440 Hertz tuning fork is held above a closed pipe. Find the spacing between the resonances, in other words, between the harmonic frequencies, when the air temperature is 20 degrees Celsius. So I know that the frequency of the tuning fork is 440 Hertz. I know if the air temperature is 20 degrees Celsius, that means that the speed of my sound wave is going to be 343 meters per second. Now I know in a closed pipe, the spacing between my resonant frequencies is going to be 1/2 a wavelength. So if I use this 1/2 of a wavelength and I combine it with my wave speed formula solved for wavelength, that is going to tell me that the resonant spacing is going to be equal to the velocity of the sound wave divided by 2 times the frequency. So 343 meters per second divided by 2 times 440 Hertz will give me a spacing of 0.39 meters between my points of resonance. Problem 17. A 440 Hertz tuning fork is used with a resonating column to determine the velocity of sound in helium gas. If the spacings between resonances are 110 centimeters, what is the velocity of sound in the helium gas? In this problem, we are again given a frequency. This time it is 440 Hertz. We are given the length between my resonant frequencies, that is 110 centimeters or 1.1 meters, and we are being asked to find the speed of the sound wave, which is in this case in helium gas. So once again, because I know that the spacing between my resonant frequencies or my harmonic frequencies is going to be 1/2 of a wavelength, and I know that distance is 1.1 meters, that tells me that my wavelength is going to be equal to 2.2 meters. If 1/2 a wavelength equals 1.1 meters, if I multiply both sides of this equation by 2, that'll give me a wavelength of 2.2 meters. Now I have my wavelength, I have my frequency, and if I have those two things, then I can use my wave speed formula to find the velocity. So the velocity equals the frequency times the wavelength. 440 Hertz times 2.2 meters will give me a velocity of 970 meters per second. Problem 18. The frequency of a tuning fork is unknown. A student uses an air column at 27 degrees Celsius and finds resonances spaced by 20.2 centimeters. What is the frequency of the tuning fork? So in this case, we're being asked to find the frequency, and we know what the distance between my resonant spaces are. And we also know what the air temperature is. So I can use the air temperature to find the speed of the wave, and I can use the spacing between the resonances to find the wavelength. From those two things, I can then find my frequency. So let's take a look. I know my temperature is given in Celsius, and I want to convert that to Kelvin. So I know that the temperature in Kelvin will equal 27 degrees Celsius plus 273. Which will give me a temperature of 300 Kelvin. To find the speed of the wave, I then use my wave speed formula, so 331 meters per second times the square root of my temperature in Kelvin divided by 273 Kelvin is going to give me a speed of the sound wave of 347 meters per second. The length between the resonances is 20.2 centimeters, which I convert to meters, so that'll give me 0.202 meters. And if my resonant spacing is 1/2 of a wavelength, and that is 0.202 meters, then my wavelength is going to be equal to 0.404 meters. I just take this equation, multiply both sides by 2, just like I did in the last problem. So now I have my wavelength. I have my wave speed. I can use my wave speed formula to solve for the frequency. And solving that formula for frequency will give me F equals V divided by lambda. 347 meters per second divided by 0.404 meters will give me a frequency of 859 hertz. Problem 19. A bugle can be thought of as an open pipe. If a bugle were straightened out, and try this at home, kids, it's fun. Get yourself a bugle, straighten that sucker out. See, if a bugle were straightened out, it would be 2.65 meters long. First thing they want you to do is find the speed of sound, or if the speed of sound is 343 meters per second, find the lowest frequency that is resonant for a bugle, ignoring end corrections. Remember, I mentioned what end corrections are in yesterday's video. So I know that the length of my open pipe, which formerly was a bugle, is 2.65 meters. I know that the velocity of the sound wave is going to be 343 meters per second. And I know the wavelength is 2 times the length of the pipe. So because the wavelength is 2 times the length of the pipe, I know that the wavelength is 2 times 2.65 meters, and that is going to give me a wavelength of 5.30 meters. So I have my wavelength, I have my velocity for the sound wave. I can use those two quantities to now find the lowest frequency using my wave speed formula. And I know my wave speed formula solving for frequency is going to be the frequency equals the velocity divided by the wavelength. So 343 meters per second divided by 5.30 meters will give me a frequency of 64.7 hertz. Part B of problem 19 asks us to find the next two resonant frequencies for the bugle. So we are looking for the frequency of the second harmonic and of the third harmonic. Remember, because this is an open pipe, we do have odd and even harmonics. In a closed pipe, we only have odd harmonics. So to find the frequency of our second harmonic, I know that is equal to the velocity the velocity divided by the length of the pipe. So 343 meters per second divided by 2.65 meters will give me a frequency of 129 hertz. To find the frequency of our third harmonic, I know that is equal to 3 times the velocity divided by 2 times the length. And remember, these two formulas here are going to be straight off of the PowerPoint. That is going to equal 3 times 343 meters per second divided by 2 times 2.65 meters, and that will give me a third harmonic frequency of 194 hertz. Problem 20. The lowest note on an organ is 16.4 hertz. What is the shortest open organ pipe that will resonate at this frequency? So my frequency is 16.4 hertz. I know the wavelength is going to be the velocity divided by the frequency, and again, we're going to assume an air temperature of 20 degrees Celsius, which would give us a velocity of the sound wave of 343 meters per second. So 343 meters per second divided by 16.4 hertz will give us a wavelength of 20.9 meters. Now I know that the length of the pipe is equal to 1/2 of the wavelength. So if I take my 20.9 meters and divide that by 2, that will give me a length of the organ pipe of 10.5 meters.